This video shows how to use Feynman's technique to solve complex integrals by introducing a parameter and differentiating under the integral sign. Less than break time equals 0.3 s greater than. This powerful method appears in advanced calculus courses and helps tackle integrals that resist standard techniques. Less than break time equals 0.3 s greater than. You'll learn to identify suitable parameters, apply differentiation under the integral, and integrate back to find elegant solutions. We'll use Feynman's trick, differentiation under the integral sign. Less than break time equals 0.3 s greater than. First, we introduce a parameter t by replacing x with x to the t. Less than break time equals 0.3 s greater than. Then differentiating with respect to t magically kills the log x in the denominator, giving us 1 over t plus 1. Less than break time equals 0.3 s greater than. Finally, integrating back gives us ln 2. Less than break time equals 0.5 s greater than. Let's work through it on the diagram. How do you integrate x minus 1 over ln x from 0 to 1? Less than break time equals 0.3 s greater than. Standard methods like substitution and integration by parts all hit a wall here. The logarithm in the denominator blocks every direct approach. Less than break time equals 0.4 s greater than, but Richard Feynman had a brilliant trick. Introduce a new parameter, differentiate under the integral sign, and watch the complexity vanish. Goal: less than break time equals 0.3 s greater than. Evaluate this integral using Feynman's technique of differentiating under the integral sign. Step 1. Less than break time equals 0.3 s greater than. We introduce a parameter t by replacing x with x to the t in the numerator. Define I of t as the integral from 0 to 1 of x to the t minus 1 over ln x dx. When t equals 0, x to the 0 is 1, so the numerator is 0. Less than break time equals 0.3 s greater than. This gives us our initial condition, I of 0 equals 0. And when t equals 1, we recover exactly our original integral I. Now comes the magic. We differentiate I of t with respect to t. Step 2. Less than break time equals 0.3 s greater than. Differentiate the integrand with respect to t. The ln x terms cancel beautifully. By Leibniz's rule, we differentiate under the integral sign with respect to t. The derivative of x to the t is x to the t times ln x. Less than break time equals 0.3 s greater than. The ln x in the numerator cancels with the ln x in the denominator. This is the magic moment. Now we just integrate x to the t, which is a simple power rule. Less than break time equals 0.3 s greater than. The result is 1 over t plus 1. I prime of t is just 1 over t plus 1. Now we integrate back to find I of t. Step 3. Less than break time equals 0.3 s greater than. We integrate I prime of t from 0 to t, using our initial condition I of 0 equals 0. I of t equals the integral of 1 over s plus 1 from 0 to t plus I of 0. This integral gives ln of t plus 1 minus ln of 1, which is just ln of t plus 1. Finally, set t equals 1. Less than break time equals 0.3 s greater than. I equals ln of 2. Less than break time equals 0.5 s greater than. That's the answer. The integral of x minus 1 over ln x from 0 to 1 is exactly ln 2. Whenever you see a logarithm or awkward expression in the denominator that blocks standard techniques, think about Feynman's trick. Introduce a parameter that generalizes the integrand. Differentiate under the integral sign to simplify. Then integrate back using the initial condition. The integral of x minus 1 over ln x from 0 to 1 equals ln 2. Less than break time equals 0.5 s greater than. Elegant, powerful, and pure Feynman.